Okay, so in this chapter itself, we're going to learn about dynamics. Now, basically, dynamics itself is actually just your chapter on forces itself. Okay, so the very first thing we must learn is what exactly is a force. Now, a force is just a push or pull that can actually change the position, speed, and state of object itself. So to make things clearer itself, the effects of a force is the one below here. There is 3 of them. This one allows you to change your speed or your motion. You can change the direction. You can also change the shape and size of the object itself. Okay, so this is the dynamics itself. So the thing is, for a force, the SI unit will actually be in newtons itself. So how do you write this? Your force will be 200 newtons. Must be capital N. Okay, please do not write small letter n. If you write small letter n, you actually minus marks. So be very, very careful. And next, your force is a vector quantity, which means you have both magnitude and direction. So it's very, very important that you note where's the direction, whether it's moving forward or moving backwards itself. Okay. Now, next, let's talk about the different types of forces. So we have your contact forces and we have your non-contact forces itself. Now, contact forces, when we say contact, it means you need to be touching or in contact with one another itself. So you'll notice whenever you have a contact force itself, all the forces are drawn from the surface of object. So you can see over here when we are pushing the box itself, when we push the box, there will actually be there will be a force over here, or you can also draw the force towards here. So basically, your applied force will be given by this, and the letter accompanied will be capital letter F. So when you push something, when you pull something, technically, when you apply a force, we typically call it an applied force. Okay. Then next, we have this is your normal force, or sometimes some schools will still call it normal contact force. Okay, so you can call it N or NCF, depending on your school. So what exactly is a normal force itself? Your normal force is a bit special. It is always 90 degrees to the surface. Okay, so you can see your surface is over here. So your normal force will be 90 degrees. Okay, over here 90 degrees. So for every contact surface area, there is a normal contact force. Okay, so you can see over here, you have one surface here, you have two surface here, number 1 and number 2. So because of this, each of them will have 90 degrees, one normal contact force each. So all of them will be perpendicular. So every object that you touch that has a contact surface area, including another object, will also have normal contact force. Okay. Next one, let's talk about tension. Tension we usually denote it with a capital T. Now, if you're pulling the box over here, how do we draw your tension? It will always be from the side of the box towards the rope tension. However, if you want to say the tension of the man, this is the contact surface area, or the contact, basically your surface area, and basically that is how it goes. Because don't forget, all of this that we're talking about are contact forces. So this is the point of contact, and therefore he will have a tension in opposite directions in this case. So you need to see, when we are talking about forces itself, what object are we talking about? What force on what object? Because that will actually tell you the direction of your force itself. Is it away from the object? Is it towards the object? And stuff like that. Okay, so how do you know if something is tension? You must have spring, string, or rope. Okay, you always be towards the rope. All right, and then next one. Okay, just wait a while this loads. Next one, you can see when this lady is actually pulling over here. When she's pulling this box, the box is moving, right? The box is actually moving over here due to tension. And what happens? Because you're dragging around a rough floor, there will be frictional force. So for frictional force, we actually denote it with a small letter F. Okay, so you can see over here, because you drag to the left, there will be a frictional force. And where do you draw the frictional force? From the middle of your box to the right. Okay, you always be in opposite directions because of this property. It always opposes motion. Okay, because of that rough surface, we know that there must be frictional forces. And next, you have your air resistance or water resistance. Now, this naming itself for air or water resistance, sometimes we use letter R, sometimes we still use small letter F. It really depends on what your school uses. But for me personally, I use R to differentiate it from friction. Okay, so because when you're running itself, what happens? You'll notice that you actually have this contact area with the wind when the wind blows against you, right? So what happens? Because of this, the wind will actually try to slow you down while you're trying to move forward with your applied force. So this is still your air resistance. And because this is a contact force, there will be at the surface over here. You can either draw it in front or behind for air resistance or water resistance. Next, for your non-contact forces, basically non-contact forces is a bit special. It's either you're touching or not touching. So it's more of an either or and not just a simple it's not touching. Because let's say if you or my favorite box is in the air, is on the ground, your non-contact forces, which is your weight, is acting on your object. But if your box is in mid-air, it will still have weight W, because weight, which is your gravitational force, is also a non-contact force. So which means that it doesn't matter whether you're touching or not touching, you can have both or either or. You will always have weight pulling you down because Earth is beneath our feet. We are actually attracted to the Earth. That's why we will actually move down or draw your arrows downwards. Okay, it's always a pulling force. It's always an attractive force. Okay, so for electric force and magnetic force itself, they are a little rare because most of these are actually set 4 topics. So when you actually reach the set 4 topic itself, they'll actually go into more in-depth about it, and they'll tell you about it itself. So for this electric force and magnetic force, you just need to, if you are expected to draw them, you just need to follow how we do it for your weight. But just take note, for electric and magnetic force, they have attractive and repulsive forces. So they're not always going to be downwards, okay, unlike your gravitational force. Okay, so next, let's talk about your mass and weight. Because just now, if you notice, we actually mentioned that weight is your gravitational force. Okay, so this is actually a force. So what exactly is mass? Okay, because if you notice, the definition for mass is the amount of substance in an object or the amount of matter in an object, and the units is kilograms. Okay, and they are not affected by location. We will use a beam balance. On the other hand, your weight is your force, and your force must be measured in newtons. So if you want to do a quick side-by-side comparison over here, mass will be kg, while weight will be newtons. And you will notice that the values, they are actually not the same. Okay, the units are different, the values are different, they are not the same thing. Okay, now in real life, sometimes we just call your friend, hey, what's your weight? What's your weight? Typically, we always say in kg, right? But now, moving on from this point on, we are now somewhat scientists. We should use newtons for weight. And if you want to ask someone about their kg, you need to ask them about their mass. What's your mass? Your mass will be whatever kg that you have. If someone asks you what's your weight, you should be saying, oh, it is actually this newtons. Okay, and how do you exactly calculate or measure your weight? We use this formula over here. Put a star next to this. We'll be using this very often. Okay, and as I always say, whenever you have any kind of formula, always make sure that they must be in SI units. Because if you don't use SI units itself, you will make careless mistakes here and there. Okay, so just be very, very careful itself. So weight is a vector quantity, which means it has magnitude and direction. The direction will always be vertically downwards. It will be towards the earth. So it really, really depends on the, and weight is affected by location. So if you're on the moon versus if you're on earth, you will have different results. Okay? And if you measure it, one of mass uses beam balance, your weight uses spring balance. Okay? So don't worry too much about this. Now, just now if you notice, we actually talk about your G. What exactly is this G over here? Now, G is this. Okay? So just now we learned that W is M times G. So what is G? G, when you move it over, is W divided by M. So what exactly is W? W is your gravitational force, correct? This is your mass. So it is your gravitational force, W, per unit mass. Okay? So basically, if you want to state your definition, you just need to change your formula into words. Okay, so your gravitational force divide is per unit, then below is your mass. So it's your gravitational force W acting per unit mass M. That's all. Okay, and take note, this is different. Okay, gravitational field. What exactly is a field? A field is just your region where you have this mass that has this force. Okay, so just take note, basically your gravitational field is just that region where you experience that gravitational force. Your gravitational field strength, this one, is how strong gravity will be. Okay, but this one is just be careful, it really depends on the mass itself. It's a ratio. Okay, it's not your weight. They're not exactly the same. And sometimes you will see that G, sometimes I call it gravitational acceleration, sometimes I call it gravitational field strength. They are actually exactly the same thing. 10 meters per second square or 10 newtons per kg. They will always be this number fixed. Okay, unless your school says otherwise, except for particular schools like RI and RGS, other schools will all use 10 meters per second square or 10 newtons per kg. If you are from RI or RGS, you have to use 9.81 meters per second square or 9.81 newtons per kg. Really depends on your school itself, what's the number that they use. Okay, so let's take a look at the work example over here. So first thing is, can you all scratch out this inertial? I actually shifted it to the back of the notes. Okay, so first thing, they tell you that your weight on Venus is W. Okay, and they tell you that G of Venus is this. Okay, and then they tell you the G of Earth is this. Okay, so they ask us to find what's the mass on Earth. So to find mass on Earth, technically we should be using, by right, we learned the formula W is mg, right? We want to use m is W over G. But now here comes the problem. We don't know what's the weight on Earth. Because whenever we use the formula like this, right, you need to make sure that you are using the mass on Earth, weight on Earth, G on Earth. All of them must be the same. But now the problem is we don't have the weight of Earth. It's actually your part B answer itself, which means most likely we cannot use this formula directly to solve. But let's take a look at what they gave us. They gave us the weight on Venus. They gave us the G on Venus. So what does that imply? It means I can actually use this formula that is given to us to find the mass on Venus. So weight on Venus over G on Venus. So let's find this number first. 550 over your 9.0. So take out your calculator and press this value in. You should end up with 650, and because this is mass, it will be kg. Okay, so now what's the purpose of using this? Don't forget, mass is the amount of substance, which means the mass on Earth is equals to the mass on Venus, because when I just move from Venus to Earth, my amount of substance doesn't change. I will still be 650 kg of mass. Okay, then at the bottom over here, W equals to mg, weight on Earth. So I'll use Earth, Earth, and Earth. So which means 650 just times 10. You get 6,500, and weight is a force, so we use newtons. Okay. So always make full use of the question. Most of the time, the amount of information given to you is just nice to solve all the unknown values. Okay. Next, let's talk about your question 2. Question 2 tells you that you have 853 people. Okay. And each people have a max baggage. Okay. And each of them is 100 kg each. So what's the total weight by at max capacity? So total weight, first thing, before we do anything, we want to find your W equals to mg, right? So we need to find your total mass. So total mass itself, first thing, we have 853 personnel. And what happens? Each of them is 100 kg each, and they carry 30 kg for max capacity, which means I will have a very large number. Okay, I'll end up with 110,890 kg. Okay, and I will not actually convert it to 3SF yet. Only your final answer only, we will use that. So 110,890, and your G. Typically, if the question doesn't say what is G, G is always assumed to be 10. So because of this, we will end up with 110,890. So we write the long version itself. Now, even though this is exact, make sure to express it in 3SF, because that's what the question asks us. And most of the time when we're actually dealing with numbers that is bigger by like more than 4 digits or less than 4 digits, like decimals, right? We always try our best to round it up to 3SF or 2SF, depending on your school itself. If you're not sure what does your school use 3SF. Okay? But some stricter schools like MGS, Hwa Chong, RI, RGS, they will follow according to the smallest SF and smallest DP. If you all need help with that, go look it up, or you can just drop the center a message. Okay? So because of this, we'll do 3SF in this case. So 1, 1, 1, 0, 1, 2, 3. And this is in newtons, bracket 3SF. Okay? So if you can, try to leave a space so that you can count it easier. So basically, this is 1,110,000 newtons. Now, next part over here, explain why the total weight carried by the bus decreases when the airplane is flying itself. Don't forget your W. Okay, so your total weight is affected. Okay, let me write it at the side. Your W equals to mg, right? So now G is not affected by location. So the only way we can affect your weight must be G. Okay, and your G will actually be affected by your height. So what does that mean? When the plane is flying, the gravitational field strength is weaker. Okay, as the plane is further away from the Earth. As such, the total weight carried by the Airbus decreases. Okay, so you just need to answer back the question itself. Because how do we know this? Because if you actually look back over here, this point, which I actually missed out, my apologies, it's actually this point over here. Gravitational force is strongest at the surface and weaker further away. So basically, the closer you are to the Earth, the stronger the gravity is. The further you are from the Earth, the weaker the gravity is. So if you want to lie to yourself, you can always go up a mountain and measure your weight on top of a mountain. Because when you're actually on top of a mountain itself, you're actually further away from the center of gravity itself. You are, okay, center of gravity, you're further away from the Earth. Okay, so because of this, you can lie to yourself. Okay, but basically the mass, the amount that makes up doesn't change. So if you go up to a mountaintop, the amount doesn't change as well. So you're really just lying to yourself when you're actually measuring your weight. Okay, so please be careful and take note that about these kind of explanation questions. Okay. Next, let's talk about friction and air resistance. Now, there's actually a term to actually sum both of them up. This is what we call your frictional forces, or we can call this resistive forces. Basically, this is the big brother. So we'll just call it frictional forces to actually use for both of them. So this is just a very, very generic term that will accommodate both of them. Okay. Now, there are two types of friction itself. That is one that we use, which is your kinetic friction. Kinetic, this word means moving. Okay, static means not moving, basically. So when you have any kind of static friction itself, this one basically means that if your object, let's say I have a slope, I have a slope, and normally I have my box sitting on top of the slope. Weight will always be downwards. Because I'm touching a surface, I also have normal contact force. Now, if you look at these two forces, one is down, one is diagonal like this, you will think that the box will actually slide down. But the thing is, the box actually doesn't move. Why is that so? Because even though the box is not moving itself, there is what we call a static friction. Okay, this friction itself will actually keep your object from moving, even though right now it's not moving. So just take note. And sometimes if you push a box, okay, when you push the box itself, now usually you have to exert a certain amount of force before the box starts to actually shift and then move in the position itself. This initial amount of force that you need to exert just before it starts to move is what you call your static friction itself. Okay, so don't worry about this too much. Basically, we just need to call it friction itself. Only certain schools will actually need to learn about static and kinetic friction, and they will also learn it at kind of like borderline, is very skin level depth of understanding. You don't need to really go in to calculate it unless you're in some kind of special program and all that. Okay, so most of the time, whenever you're talking about kinetic and static friction, you don't need to worry too much. It just means friction. That's all you need to know for your syllabus. All right, now on to more important things. Friction will always oppose relative motion. Now, if you notice, I actually added this word relative. So some students be like, "Cher, do we really need to write relative?" Yes. Why is that so? Because if you use a box example, it's very straightforward. We all understand what is it. But if you look at a ball or any kind of like circular object, they will be slightly different. Okay. And for the last property of friction itself, the faster the object, the more frictional force that is stopping you. That's why typically if you're running, when you run, you feel the wind blowing against your face, right? That's actually the air resistance that's increasing and trying to stop you from running so fast. Okay. Now you have three different types of friction itself. You have your sliding friction, which is the standard one. We will draw it from the middle of the box. Okay, maybe I use blue color to make it clearer. You will use this F. Okay, and if you look at a wheel, when you look at the wheel will turn in this direction, correct? So where is your contact surface area? Contact surface area is right at the bottom. So where would my friction be acting? Friction will always be opposite to the direction of relative motion itself. So your friction will actually be to your right, which is very weird. But because of this, friction actually helps us move forward when we are actually using a wheel. That's why typically if you want to move something easier, you actually put wheels onto it so that it can roll and travel easier. All right, now here comes the trouble. Let's say I have a car, okay, a not very nicely drawn car, but your car is moving to your right. Now, there is a few types of question that you ask. What is the direction of friction on the car? The direction of the friction on the car, when we do look at this kind of question itself, we'll treat the car as one box. Okay, so if my box is moving to the right, where's my friction? My friction will definitely be to the left. This is friction. Now, what if the question change? What's the direction of friction on the wheel of the car? Then we need to focus on the wheel part of the car. So because my car, the wheel, right, is moving to the right, so what happens? You need to draw like this. Because you turn clockwise, right? So what happens at this point in time? Your friction will be to your right. So how do you know what's the question to answer? It is the object that we are focusing on. Is it the car or is it the wheel? If they ask you for the entire object, just treat the entire big object as one big box. That's all. Then you just need to know, are you moving to the right? Are you moving to the left? My friction will just be always going to be opposite to that motion itself. Okay? It doesn't always have to be a ball. It doesn't always have to be a box. Even it can be your own foot. When you're walking. Now, take note. Let's just try to imagine. Just if you are at home, feel free to just stand up when you walk. Now, when you walk, your body is moving forward, but so that the friction on you will be backwards. Because you're moving forward, friction on you will be backwards. But let me change the question. What's the direction of friction on the foot? On your foot when you're walking? If you notice when you walk, what happens is that your foot is actually moving backwards. Okay? So when your foot is moving backwards, what is the direction of your friction itself? Friction will actually be forward. That's why when we walk, even though our foot is moving back, friction is the one that's actually pushing us forward. So what does that mean? Without friction, we cannot walk. Okay, so it's some food for thought. So last but not least, don't forget we have 3 different types, right? And the last one is actually what we call fluid friction. This is actually just your air resistance and water resistance itself. Okay, so if you're falling, air resistance will just be in the opposite direction. It will be upwards instead of you're falling downwards. Okay, so you can see over here, I want you to take note. When you want to say any advantage about friction is that you can walk without slipping, you have firm grip of objects, you can slow down and stop vehicles, and basically the rest. Okay, now for this one, rubbing hands to produce warmth, it is very, very specific. Because if you're in a very cold place, you rub your hands, warmth is something that you desire. Okay, this is something that must be desirable. Something you want. Okay, but on the other hand, for disadvantages, most of them are just wear and tear and energy losses. Okay, so the thing is, how do you know which one to use, which one not to use? Undesired is the keywords over here. Only when these are things that you don't want, then those are disadvantages. Okay, because sometimes we can make full use of friction for something good. Sometimes we can make sometimes walking without slipping or firm grip itself can also be a disadvantage. One of them, for example, is if you fall down and you you fall down and you hit your hand against a parade square, those kind of very jaggedy parade square, what happens to your skin? Your skin will actually tear and you will start bleeding, right? And that will actually change the firm grip on the floor into a disadvantage. So it really, really depends on the context, on how you describe the scenario itself, whether this is an advantage or disadvantage itself. Okay, so because of all your advantages and disadvantages, you will want to learn about methods to increase or reduce frictions accordingly. Now, when we talk about these threads itself, right, basically what I mean is, sometimes you see the screws, right? They actually have these kind of spirals. These spirals are what we call your threads. Or sometimes even your tires, your wheels itself. Okay, I'm not very good at drawing, but basically these are your tires. So some of your tires, they have this kind of funny extra patterns, right? Those patterns are your threads. Basically, they increase your contact surface area. So like your shoes, the bottom of your shoes, they have a certain pattern itself. Those patterns, not just for design, they are also there to actually increase your contact surface area. So when you walk, you don't slip and fall. Okay? Then for wheels and ball bearings itself. Now, if you notice a wheel or any kind of round object itself, the contact surface area is actually very, very small. So what does that mean? It means less friction. So sometimes it's a good and a bad thing. So you need to kind of figure it out whether you want more friction or less friction itself. So basically, if you think about it, if you do the opposite of what is on the left-hand side and the right-hand side accordingly, you actually get the opposite results as well. For example, you smoothen and polish a rough surface, you can also roughen a smooth and polished surface if you want to do the opposite. Okay, so a lot of different things that you can do just to do and achieve the opposite results. So really need to go back and just ask yourself, what is the use of friction in my day-to-day life? What have I been using? If you notice, if you're holding a mouse, if you're holding a pen, a pencil, that holding itself is actually your firm grip on objects. If you want to walk around, you want to move around, you need to walk already. And if you actually use your pencil to write, or even your pen, just to be able to write something, you need to have friction, because the pencil itself works based off friction itself. Okay? So a lot of different things. Your disadvantages are your wear and tear as you keep using your items over and over again, like your pencil. The tip of your pencil will get more and more blunt over time, right? So similarly, your shoes, if you keep wearing your shoes, you might actually damage your shoes and the bottom gets more and more flatter and flatter. So you'll feel that as you wear your shoes for 2 years plus, you feel like it's very, very slippery at the bottom of your shoe. You take a look at the bottom, it's actually very, very flat now. So because of this, you actually have all your different advantages and disadvantages of friction.